Welcome. In this video, we'll walk through the steps of creating a thermal analysis of your heatsink model and then walk through a few design changes that you may make to test to see if you can increase its effectiveness. First of all, I'm going to open up the CAD file that we created previously before we put any solution on it. This is just the minimal viable product, which is a great starting point. We want to know what's our baseline effectiveness, and then we're going to try to improve it from there. First things first, we should change some of the options here if you haven't already done so by going up to the File menu and down to Live Options to make sure the units match the ones that we're familiar with. So down here on the left-hand side we have units, and I put it back into imperial units so that we could get the dimensions of the aluminum to match the ones that we purchased from the mill, was in inches. If you go down in the menu here, you've got some units for the physics that we can adjust independently. For example, let's put temperature to degrees Celsius, which is what the client asked us to kind of work with, and then the heat flux. This is going to be the thing that we're trying to maximize with our design. Right now it's in British thermal units, or BTUs. Let's go down and look at some of the other options here. The last one is the most standard international units here, a watt per square meter. And a watt would be a joule of energy every second coming out every square meter of area. So let's choose that bottom one there. Hit OK. The work here again, if you've worked straight through the other videos, you'd want to make sure you've got this saved before you start making any modifications, because you always want to return back to this basic starting point in case anything goes wrong or you're trying to compare to a baseline model. So save now if you haven't. One of the things that happens in Discovery Live, when we add this rod to the cube on top, it actually makes it one body. Previously, I told you that you could ignore some of the options over here. This top one right now, though, we're going to peek inside and see it has only one solid object there, one body. And for our purposes, it'll be helpful if we have it split into two bodies, the cube and the cylinder, still physically touching, but considered to be separate. The way we're going to do that is by going up to the Design menu, and then about halfway over you see the option to split the body. So choose that. There's always useful tips up here at the top. The first thing it asks us to do is click a target object. Well, we only have one body, so that's got to be our object. Then it says to click a face or plane that we're going to use to cut these. And so if I hover right here on this face between the cube and the cylinder, it kind of shows me the plane that exists there. That's where I want to separate these two. So I'll click that once. The third and final option it tells us to do is to click the region we want to remove. So we could delete one of these right now, but I want to keep both of those, so I'm just going to exit out of this active tool. Now if I go and peek at this structure tree one more time, I actually have created two separate bodies for our design here that we can treat separately. That'll be useful. What we're going to do for our solution here, our thermal analysis, we're going to apply a heat to this bottom rod similar to boiling water, because this will be the part inside our hot cup of coffee or our hot drink. And then we'll look at how heat is transferred to the environment from the top part here through convection mainly. So let's begin by creating our solution. The options here, the left-hand one by default is the thermal behavior, so that's the one we want to keep it on. And let's pick this material aluminum. The specific heat is a little bit different from what we measured in lab, but we can adjust that in the material libraries later. Just like in the other solutions, we have to set up some boundary conditions before it gives us any meaningful data. And one extra step, because I split this into two bodies, it wants to know what is the bodies that we're conducting this on. And for our analysis, I want to do both of these. So I'm going to select both with the box dragged around them, or you could do Control A on the keyboard. Let's confirm that. Now we've got our menu options here for the solution, plus the kind of start buttons down at the bottom. Pressing play at this point won't do anything color-wise because we haven't told it some of the fundamental conditions that we need. The most important one here to get started is to tell it that this is at 100 degrees Celsius, boiling water. So if I click once on the cylinder, we get the small contextual menu. On the left-hand side, during the structural analysis, these options were things such as applying a force or defining a new fixed face. Now we see they all apply to thermodynamics. So let's just do the top one and say a new temperature on this face of 100 degrees Celsius, as if it was in boiling water. Now if I press play, we actually do get some color coding to show us what's going on. The entire cylinder is at the maximum temperature of 100 degrees, but the top cube here has a gradient. We see it gets cooler as it reaches the top of the cube because it's convecting energy as this heat flows through that entire distance. Not a whole lot of change in heat right now, only about 0.6 of a degree by the time we get to the top. So lots of room for improvement in our design here. The next thing we're going to do is to put a probe on here so we can track how heat is being transferred to the environment as we change some of the aspects of this, maybe putting fins on or drilling some holes into it, the things that you're going to do on the mill and the lathe. And the way that we're going to do that is beginning not by clicking on the body and using this contextual menu, but actually going over to our little solution menu and clicking on that similar symbol right here. This is going to give us a few more options for setting this up. The menu that pops up, there's a tiny little more link, and we want to open that up because we have to define some very specific things here. First of all, look at the results. We're not going to track the temperature on that cube, but instead we're going to look at heat flux. So remember, heat is a change in thermal energy moving from one place to another, in this case from the hot cup of coffee out to the environment, and flux just means a measure of the amount of something moving through a surface area. So it'll be looking at the heat flowing out of the faces from the cube. Secondly, we're going to change what component we're looking at. Right now it's only looking at X, and if I look at my little axes down here, X is just left and right. So the probe right now would only be looking at heat that flows out in this direction, but this is three-dimensional, so we want to make sure we're looking at both the X, Y, and the Z direction. So we can do that by going down to the sum option at the bottom of the menu. The third and final thing we need to do here is the location type. In this option, we're going to drop it down and select body so that if we add new faces to the body, it will automatically include those. If we put a valley into the cube at the top there, the internal faces won't get included right away unless we select this option here, body. So quick summary, make sure this is heat flux, make sure this is sum, and make sure this is body. We'll go ahead and hit select at this point. Now it wants us to select a body to put this probe on, and we're going to put it up on the upper cube. Once that's selected, hit the check mark here to confirm, and we get our chart to track our changes. The point now, we can kind of see what's the starting value for our design here. It looks like it's transferring about close to 3,000 watts for every square meter of surface area. Obviously, we don't have a square meter of surface area on this cube. It's only 1 inch across on each face. So this is doing a good job of really kicking a lot of heat out to the environment. But let's see if we can make that number go even higher. One thing I'll model is putting a ridge or a valley down into this design by sketching on one of the faces with the rectangle tool. First click here selects the face that we want to sketch on. I'll do it from the top. Next, I have the option to actually draw this out, and I'll just go from one edge across to the other. Now that I've got this defined box, I can use the pull tool to kind of push that down into the design. I'm going to keep this graph open so we can see what's happening. Sometimes by defining that face on the surface, you actually see a decrease in the effectiveness. It doesn't hurt to open up your calculator here right click on the calculator here to clear the information that was on there after adding that face. From here on out, we should intuitively see as we increase the surface area, there is a increase in the heat transfer to the environment. So I've got 2 design changes there. The third one, that's also increasing, making it even lower. It's still going up, but starting to level off. So there seems to be some kind of point of diminishing returns where if I go too far, it becomes less effective, perhaps because the heat has to flow through this narrow bit. Let's explore putting a hole through one of the faces here and see how that affects it. Again, I'm going to come over to the sketch tool and select the circle option, which looks very similar to the polygon. Because I had the bottom of the valley selected there, that's where it thinks my sketch plane is going to be. So let's reselect a sketch plane that's perhaps on this side, and we'll push it in from this direction. The circle tool is now active, so let's just kind of make one somewhere in the middle here. Again, going back to the pull tool, I'm going to push this all the way through, and if it touches the other side, that makes it a hollow space. Yeah, there we see a big jump in our data. If we want to see specifically what the value is now, you can always collapse the chart with this little up arrow, and there it tells us what the current value is. The next thing I'm going to do is show you that you can extend other shapes off of this object. So let's put another rectangle on this face, but instead of pushing it into the design, we'll push it out. See what that does for our effectiveness. So just like when I made the valley, I first start by creating a rectangular face. I'm going to select this and use the pull tool, pull that out, That's a huge increase in effectiveness there. So if we're able to add extra external materials or fins to our device, that seems like it's going to be a really good design choice. Collapse this value and see what our value is now. 4,000, that's going up, and it's going up quickly. So hopefully this is enough to help you understand how to start by setting up our probe on the surface correctly and getting quantitative values out of it. To summarize this last bit, this says that 4,500 joules of energy are being transferred every second. So joules per second is a watt for every square meter of surface area that we have on this device.